Let us start. We have a square cross section bar of side A, and the bar is initially loaded as its two sides vertical and two sides horizontal. Now the same bar, same type of bar, similar bar is loaded. Its uh, diagonals, one of the diagonals are kept vertical and other one is kept horizontal. They are loaded in similar way, and our task is to find the ratio of their moment of resistances. Now moment of resistance M can be found out by the formula sigma into Z, where the for maximum M it will be maximum sigma and Z will be the section modulus. Now the sigma will be same as both of the bars are similar, made of same material, so sigma will be same, but M will be different due to Z is different. So in both the cases we will find out Z. The Okay, so we were going to find out the section modulus for case 2. For this case, when the diagonals, one of the diagonals are vertical and one of the diagonal is horizontal. So in this case, when you find out I2, that means the the moment of inertia of second case. So in this whole section can be divided into two sections, section 1 and section 2. Both are triangles and they have similar dimension, so we just multiply 2 with one of the dimensions. So for this first one it will be bh cube by 12. This is the formula for moment of inertia of a triangular section about its base. So bh cube by 36, where b is the base, so this will be one of the diagonal, and one of the diagonal can be found out this way. This is a right angle triangle, one side is a, this side and this side is equal, so this will becomes a by root 2, and this will also becomes a by root 2, this will also become a by root 2, this will be also a by root 2. Okay, so now here section modulus the section modulus is 2 into bh cube by 12, so base is equal to 2 into a by root 2, so this will be root 2a, this will be base into h cube by 12, h is a by root 2 bh cube by 12 divided. Here for triangle the formula is bh cube by 12 about base in case of a triangle. So we will just use that formula here. This is b, this is h, so this is the I2 by y max will be equal to from here to here that will be a by root 2. So now we can find that Z2 will be equal to, upon solving, a cube by 6 root 2. So now then M2 becomes sigma into Z2. So here we have found out Z1, M2 will be into a cube by 6 root 2. So when we place M1 by M2, this becomes sigma into a cube by 6 divided by sigma into a cube by 6 root 2. So this will become root 2. So answer will be 1.414. Is the video again stopped? Okay. So we can find that if the same bar being used for same type of loading, but initially two sides were vertical and two sides were horizontal, later on one of the diagonal is vertical and other diagonal is horizontal. So the same bar is used in different ways, and we have find the moment of resistance will be different. So the load bearing capacity, bending moment, supporting capacity will be different, and the ratio will be 1.414. So for the same beam, due to the use of it, we can get different moment of resistance. So now if we use a rectangular bar where it's one of the side is B, other side is D, in this case it will be BD cube by 12. But when in this case B is greater than D, but when we will use it by rotating 90 degree, here this is B and this is D, the same bar, we are just using it with 90 degree. We will find in this case the moment of inertia will be dB cube by 12. Okay, here also B greater than D, same bar, same case. So you can find that in this case, when the bigger dimension is taken as depth, then this moment of inertia becomes higher and the load bearing capacity is higher. So whatever we use, whatever beam we use the shape as such that the depth is greater. So the much we depth make greater, it varies, the moment of inertia varies by its cube. So it will follow a cubic curve, and if you increase the depth of one bar, its capacity to support stress rises by the depth is the cube of the depth is taken when you are finding out the moment of resistance. So when the designer has designed it, you will find the girders or the supporting long supporting bars under the flyovers. You will find there are beams are used which having more depth than their width. Generally I section is used. You will find below the flyovers, you will find there are I section beams are used. So to the reason behind it is, for I section this moment of inertia we get is higher. For the same weight, for I section rather than other sections, the I section have more moment of inertia. So as a result, the I section can support more load comparing with the different cross section bars of same weight. So we can find moment of resistance by weight ratio is higher in case of I section. So that's why in all load bearing cases like flyovers, bridges, generally I section is used. Now we'll go forward and we'll we'll learn composite beam or fletched beam. Okay, this means basically when you want a very large strength, but a material you have is a very that not much stronger. Suppose you have wood as your material, but if you want to get your required strength, a very large piece is required to support that load. So in that case, that wood is being reinforced, that wood is being supported by two metallic beams or two steel beams, and in that case it will be called a composite beam. So composite beam together work as a uh, same single beam. So now we have say a wooden beam, and this wooden beam uh, is supported by two steel beams. Okay, so this is attached outside. So composite beam is basically a beam made up of two or more different materials assumed to be rigidly connected together and behaving like a single piece is known as a composite beam or fletched beam. Now these are the steel bars, and say these are say wooden bar. Okay, these are say annual rings, so that you can understand this is wood and this is outside there is steel. So let us call the wood is 2 and this material 1 is called steel. Okay, so this is steel and this is wood. So when they are properly adhered with adhesives or nut and bolts, by some mean they are rigidly fixed. So in such case, two sides are supported by steel beams. Now say the thickness of the steel bars are T and the width of the wood is B and the depth is same for both the material, which is D. Now looking at the symmetry, this will be say neutral axis. Okay, now in this case if we want to find out what will be the total moment of resistance, we will go for a quick derivation. In this case, as these two beams or two plates are rigidly fixed with the wooden beam, and they are if they are bent by means of some bending stress, then the strain in this both in all these three bars will be same. In these three plates will be same. So basically this is the cross section. It will look like this. This is the cross section and this is the steel on the outside and there is wood in the inside. So now if we apply bending load on it, the strain will be equal for steel and wood. So in such case we can write, in this common surface here or here, the strain will be same. So at the common surface, the strain is same. Now the strain for material 1 is sigma by, say sigma 1 by E1. For this wood it will be sigma 2 by E2. Strain is equal, strain can be written as stress by elastic modulus. So from here we can find a relationship like this, E1 by E2 into sigma 2, and this can be again rewritten as sigma 1 is equal to m into sigma 2, where m is the ratio, or called m is called modular ratio. Modular ratio means the ratio of elastic modulus. Now we have relation bending equation that m by I is equal to sigma by y. So from here we can write m is equal to sigma by y into I. Now in this image the value of y will be same because both the bars having d by 2 distance from neutral axis, the last fiber having d by 2 distance, so y will be equal to d by 2. Now for both the materials we can write m1 is equal to sigma 1 by y into I1, and for case of other material we can write m2 is equal to sigma 2 by y into I2. So we are not changing y because we know the y value is how much, d by 2. From this diagram we can understand it will be d by 2. Y will be equal to d by 2. So that's why we are not changing it. Here also y, here also y. So now we can write that the total moment of resistance of the composite bar, which is denoted as m, will be summation of m1 plus m2. We put the values sigma 1 by y into I1 plus sigma 2 by y into I2. So now sigma 1 can be replaced as m into sigma 2. We have already found out. So here we can write sigma 2 by y taken common, m into this is multiplication, m into I1 plus I2. So from here we can say if only material 2 is being used, then I2 plus m into I1 can be used as equivalent moment of inertia. So with this equation we can write this term m into I1 plus I2 can be treated as equivalent moment of inertia if only material 2 is used, which will give the same amount of moment of resistance as the composite beam. Okay, so we can write I, which is equivalent moment of inertia, is equal to m into I1 plus I2, and in that case m can be written as sigma 2 by y into y, where I is equivalent moment of inertia if only material 2 is used. Now this thing can be used in problem. Now as we can understand from here, this can be done by multiplying the dimensions of material 1 in the direction parallel to the neutral axis by m. We will solve it. We will discuss it with a problem. Okay, we will go for a quick problem solving session on a similar problem. Let us have a wooden beam which is reinforced by two steel plate. Okay, this is called wooden joist. These are steel plates. This is also steel plate. These two plates are supporting the joist at the middle, having 1 centimeter thickness of these plates and 10 centimeter thickness for this joist. Okay, neutral axis will be from the middle. As we can see, the depth is 20 centimeter. Okay, this is neutral axis, depth is 20 centimeters, so all the dimensions are given. A fletched beam FLITC edged ED, FLITCH ED, this is also called fletched or composite. So fletched beam consists of a wooden joist 10 centimeter wide and 20 centimeter deep, strengthened by two steel plates 10 mm thick and 20 centimeter deep as shown in figure. If the maximum stress in the wooden joist is 7 Newton per millimeter square, so sigma 2 max here is 7 Newton per millimeter square given, then find the corresponding maximum stress attained in the steel. So sigma 1 you have to find out corresponding sigma 1 you have to find out. Find also the moment of resistance of the composite section. Okay, find m and okay, fine. So let us go with the problem. Dimensions are given. One stress is also given. So maximum stress in the wood is 7 Newton per millimeter square, and elastic modulus of steel is given 2 into 10 to the power 5 Newton per millimeter square, and for wood is 1 into 10 to the power 4 Newton per millimeter square. Okay, now our job is to find first the corresponding stress in the steel. So we know in this case on the common section the strain will be equal, and as we have learned earlier, when strain is equal at the common section, then we can write the strains are sigma 1 by E1 will be equal to sigma 2 by E2. This formula can be used. So from here we can find sigma 1 will be equal to E1 by E2 into sigma 2. So E1 by E2 is given, look for here, E1 is basically steel and E2 is wood. This is 2, say this is 1. So in that case here this E1 by E2 will be 2 into 10 to the power 5, means 20 into 10 to the power 4. So that means it will be 20 into sigma 2 is 7. So this will be corresponding stress at steel bar will be 140 Newton per millimeter square. Okay. Now if we go for the second problem, then we can use the formula. So this is our answer number 1. Now answer number 2, we have to find the total moment of resistance. For that we can find out equivalent moment of inertia that we have discussed earlier, m into I1 plus I2. M is E1 by E2 and which is 20. From we can understand these values are given. M is equal to E steel by E wood, that is 20 into 10 to the power 4 by 1 into 10 to the power 4. Unit will be crossed down each other. So this finally becomes 20. We put the value here, 20. I2, sorry, now we have to find out I1 and I2. So I1 will be equal to BD cube by 12, but it is having two different plates. One is left and another one is right. So 2 into B is 10 millimeter, 1 centimeter means 10 millimeter, into D 20 centimeter. So 20 centimeter means we convert into millimeter. So we just do it in centimeter, later I will convert it. So 1 into 20, so 2 into BD cube by 12, this much centimeter to the power 4. Upon calculation we will get 133.33 into 10 to the power 4 millimeter to the power 4. So from centimeter 4 to millimeter 4, 10 to the power 4 is being multiplied. Now this is I1. I2 will be equal to, for wooden joist, BD cube by 12, B is 10 centimeter and D is 20 centimeter. This is cm to the power 4. Now convert it with calculation, 0.66 into 10 to the power 4 millimeter to the power 4. Okay. Now put the values over here, I1 and I2. You will finally get to the power 4. So this much millimeter to the power 4. Now the calculation need to check. Okay, calculation, I'm not taking guarantee about the calculation. However, now you have the formula m equal to sigma 2 by y into I. Sigma 2 we know is 7 into 7, and I is 10 to the power 4 into this much by y is equal to d by 2. So 20 by 2, 10 into converted into millimeter, as we have all converted into millimeter. Finally, we will get the value 2.4 Newton meter. Okay, so we will get the answer in Newton millimeter, and finally we have converted into Newton meter. Okay, so this is one method. If the connection get closed, please rejoin. I'll request everyone, if the connection get closed, please rejoin. Okay, this is one method. Now there are other methods too, like we can find out M1 and M2 separately, then add them. If we want to find out the resistance offered by this fast by steel plates, then what we can do, we have our formula sigma 1 by y into I1. Sigma 1 is, we can get 140, we have found out, by y is